The theory of constraints, a simple explanation. Let's talk about the theory of constraints, also known as TOC. First, a bit of history. The theory of constraints was developed in the 1980s by Dr. Eliyahu Goldratt. He shared his ideas through a popular book called The Goal. Dr. Goldratt was a physicist who used science to solve business problems. His main idea? Focus on the biggest problem or constraint and fix it to improve everything else. Now, what does it mean? Think of a chain. It's only as strong as its weakest link. TOC says the same thing about a business. Whether it's a factory or a supply chain, there's always one main thing slowing everything down. TOC helps you find that bottleneck and make it better. That way, the whole system works more smoothly. Let's look at how TOC is applied. It follows 5 simple steps called the 5 focusing steps. Our first step is to identify the constraint. Find what's holding everything back. It could be a machine, a person, or even a rule. Our second step is to exploit the constraint. Use the bottleneck as efficiently as possible. No waste, no waiting. The third step is to subordinate everything else. Adjust all other parts of the system to support the bottleneck. The fourth step is to elevate the constraint. If it's still holding you back, add more capacity, like new equipment or staff. The fifth step is to repeat the process. Once one bottleneck is fixed, find the next one. Improvement never stops. Next, here are the key benefits of TOC. The first benefit is increased throughput. More output means better results. The second benefit is reduced inventory. You only keep what you really need. The third benefit is shorter lead times. Customers get their orders faster. The fourth benefit is better decisions. You know exactly where to focus. The fifth benefit is higher profits, less waste, more output, more money. And the sixth benefit is improved communication. Teams work better when they know the goal. Of course, TOC has some disadvantages too. The first downside is that it can oversimplify things. Some systems have more than one bottleneck. The second issue is a short-term focus. You might miss long-term improvements. The third problem is resistance to change. People may not like new ways of working. The fourth risk is wrong identification. Fixing the wrong constraint won't help. And the fifth challenge is that TOC is not one size fits all. It must be adapted to each business. Let's look at some real-world examples. Tata Steel used TOC to improve one of its steel plants. By fixing a bottleneck in the rolling mill, they increased output by 15% and reduced lead time by 20%. Philips, a global electronics company, used TOC on an assembly line. They fixed a slow testing station and reduced invento. They also improved on-time delivery by 10%. Other companies like Boeing and healthcare systems have used TOC to manage projects, reduce delays, and improve patient flow. Now, which industries use TOC the most? Our first sector is manufacturing, where TOC began. It's used to speed up production lines. The second sector is supply chain management. It helps improve the flow of goods and reduce delays. The third sector is project management, using a method called critical chain project management. The fourth sector is healthcare, where it improves patient care and cuts wait times. The fifth sector is retail, helping with stock control and faster deliveries. And finally, service industries also use TOC to improve how they serve customers. In short, TOC is a smart way to improve any business by focusing on what's holding it back the most. Instead of fixing everything at once, you fix what matters most and see big results. Now let's understand famous concept called as drum, buffer, and rope in theory of constraints. The first concept is drum. Think of the drum as the bottleneck, the slowest step in your process. It sets the rhythm or pace for the whole system. just like a drummer sets the beat in a band. Everyone else should work to that same rhythm, not faster, or else things pile up. The next concept is the buffer. The buffer is a small amount of extra inventory or time placed before the bottleneck. This ensures the bottleneck never stops working due to missing parts or delays. It protects the drum from interruptions. And finally, our third concept is rope. The rope is like a signal or control system that tells the earlier steps when and how much to produce. It stops them from working too fast and creating too much inventory. It's like a rope tied from the bottleneck backward, controlling the flow of work into the system. Let's understand the concept of drum buffer rope with a simple toy production line. Imagine we have a process that starts with cutting plastic parts, then painting them, followed by assembling the toy, packing it, and finally shipping it out. Now, let's look at the flow. Our plastic part cutting stage can handle 200 parts per hour. Painting is slightly slower, with a capacity of 190 parts per hour. Then comes toy assembly, which is significantly slower at 140 parts per hour. After that, packing picks up again to 190 parts per hour. And finally, shipping matches the start of the line at 200 parts per hour. Here's where drum buffer rope comes in. In this method, we treat the slowest process, the constraint, as the drum. In our case, that's toy assembly, which can only handle 140 parts per hour. This stage sets the pace for the entire system, just like a drum sets the beat for a band. To make sure this bottleneck is not impacting entire work, we place a buffer before it, a small stock of parts that ensures the assembly line always has something to work on, even if there's a minor delay in painting or cutting. And finally, the rope is the communication or control mechanism that ties everything back to the drum. It ensures that upstream processes, like cutting and painting, don't produce faster than what the assembly can handle. So, instead of everyone working at their own speed, they align to the drum beat set by the slowest step, assembly. So, to improve the entire process, we need to focus on major bottleneck, which is assembly process in our case. So, here we need to add more capacity that matches our previous steps output. For an example, if we increased labors in this process to make 190 parts per hour, then we are good with keeping the entire momentum and producing more output. So simply by using the drum buffer rope method, we avoid overproduction, reduce waiting time, and keep the flow smooth, focused on the real bottleneck in the system.